Welcome to this explainer. Today we're unpacking the cutting-edge world of edge computing. We're going to do this by walking through an accelerated masterclass structure, drawing directly from a brilliant short-term training program designed by Dr. Bibudatta Sahu from the National Institute of Technology, Rourkela. If you've been wondering how the massive flood of data from our modern world is actually processed in real time, you are in the perfect place. All right, let's dive right in. To really grasp why edge computing is such a game changer right now, we first got to ask a pretty fundamental question. Why are our traditional centralized cloud computing models suddenly buckling under the pressure of our interconnected world? For years, the cloud was the ultimate answer, but the rules of the game have totally changed. Think about it. We're dealing with millions of sensors, smart vehicles, and real-time apps that demand split-second processing. Relying entirely on some distant cloud server exposes three massive bottlenecks. You've got high latency, you've got severe bandwidth limitations as networks get totally clogged, and honestly, you've got growing privacy concerns when highly sensitive data has to travel halfway across the country just to be analyzed. So to tackle these bottlenecks, we're taking a quick tour through this masterclass curriculum. We'll hit the cloud computing bottleneck, enter the edge paradigm, cover system design and modeling, explore resource management algorithms, look at securing the edge ecosystem, and finally wrap up with real-world applications and outcomes.
Part 2. Enter the edge paradigm.
Edge computing is a complete paradigm shift. Instead of hauling all your data up to a centralized cloud, you literally bring the computation to the data source. It bridges the gap between academic theory and real-world execution by moving the brain of the operation out of the distant cloud and parking it right next to where the data is actually being generated. That means incredibly fast, ultra-efficient processing for decisions that simply have to happen in real time. Picture a 4-layer architecture. At the very bottom, layer 1, you've got your IoT end devices, stuff like sensors, cameras, wearables, and cars. Instead of bypassing everything to hit the open internet, they talk directly to layer 2, the edge layer. This is where that low latency magic happens through local edge servers and gateways. Need a bit more muscle? The request moves up to layer 3, the regional fog layer, for intermediate processing. And finally, sitting at the top in layer 4 is your traditional cloud data center, which is now mostly reserved for heavy global analytics and long-term storage. You can really see the evolution playing out here. We started with massive, centralized cloud storage, moved down into the intermediate, regional processing of fog servers, and finally arrived at the ultra-low latency processing happening right at the edge. It's an evolution entirely driven by our absolute need for speed and efficiency.
Moving on to Part 3, system design and modeling.
You can't just throw edge servers at a problem and hope for the best, right? Engineers have to rigorously model these workloads. They look closely at 3 key metrics. First up, data size. Exactly how much raw information is that sensor spitting out? Next, latency limits. How fast does the system need an answer back to stay functional and safe? And third, computation needs. How much raw CPU or GPU power do we actually need locally to crunch those numbers? Building out these environments requires some very specific technological building blocks. Developers lean heavily on a service-oriented architecture to break applications down into manageable microservices. They use containerization, think Docker, to package the software so it can run smoothly anywhere. And they establish rock-solid edge data processing pipelines to keep data flowing logically from the sensor through the server and back. Which brings us to Part 4, algorithms for resource management. Now, the real secret sauce of edge intelligence is a concept called task offloading. This is the critical moment where the system asks itself, hey, should I process this task locally on this weak little IoT device, or should I kick it up to the much beefier edge server? These offloading strategies can be static, meaning they follow a strict set of predefined rules, or they can be dynamic, adapting on the fly based on current network traffic or how much battery the device has left. And this is where it gets pretty wild, because edge environments are inherently constrained. They don't have the infinite power and massive cooling systems of a data center. So these scheduling algorithms are constantly performing this multi-objective optimization balancing act. They're juggling 3 massive priorities in milliseconds: minimizing latency to avoid lag, saving energy so the device's battery doesn't instantly die, and maintaining a high overall quality of service. It's a seriously complex mathematical dance happening totally behind the scenes. Part 5, securing the edge ecosystem. This is a massive hurdle. Think about it. When your computing was centralized in one big cloud data center, you could just build a giant digital moat around it. But a decentralized edge network, that opens up thousands of new attack surfaces. Every single smart traffic light, every wearable device, every local gateway is a potential entry point for malicious actor. Making security and trust actually work here is a huge challenge for engineers. To lock these distributed systems down, developers have to be incredibly proactive. They start by strictly defining threat models to anticipate exactly how an attack might go down. They roll out advanced privacy-preserving mechanisms, so even if data is somehow intercepted at the edge, it's basically gibberish to the attacker. Plus, they heavily enforce secure communication protocols to guarantee trustworthy computing across every single layer we looked at earlier. All right, wrapping things up with part 6. Real-world applications and outcomes. Edge computing isn't just some abstract academic exercise. It's practically the invisible engine running our modern world. It is the driving force behind low-latency innovations in healthcare monitoring, where an irregular heartbeat needs analysis instantly, not after a round trip to a cloud server. It's powering smart city traffic grids, managing the hyper-automated factory floors of Industry 4.0, balancing the smart energy grid, and critically, it's exactly what allows autonomous vehicles to make a split-second braking decision when a pedestrian suddenly steps into the road. The ultimate goal of Dr. Sahu's masterclass, and really the main takeaway from our explainer today, is bridging that gap between theory and reality. It's about taking these core principles of architecture, resource optimization, and security, and using them to equip engineers with the practical skills to actually analyze and deploy real-world, edge-enabled intelligence systems. We've seen how edge computing flips the traditional cloud model completely upside down to give us the speed, the privacy, and the efficiency that today's tech demands. With the limitations of the centralized cloud in the rearview mirror and the immense decentralized power of the edge right at our fingertips, the landscape is wide open. So I'll leave you with this thought. As this ecosystem expands into literally every facet of our daily lives, what real-time, low-latency future will you help engineer?